Welcome. We are discussing the second chapter, Calculus of Scalar Fields. Now we are going to start the seventh module, Gradient of a Scalar Field. In our earlier discussion, we observed one thing. When f was a scalar field which is differentiable at a point A, then several times we considered a vector del f del x1 a del f del xn a, which is a member of Rn. This is called the gradient of the scalar field f at the point A. It is a very important part of our study. Now we are going to start this. We start stating the learning objectives. From this module, we shall come to know what do we mean by gradient of a scalar field. Then we shall study some properties of gradient. This will be followed by stating the importance of this gradient. And finally, we shall mention the relation between derivative as a real number as well as a linear transformation for single variable calculus. We start this module by discussing certain results from linear algebra which we shall frequently use. First result. Let A be a vector in Rn such that for every choice of y in Rn, inner product of Ay is 0. Our claim is that A is nothing but the 0 vector. Given for every y in Rn, inner product Ay is 0. So, in particular, let us put y is equal to A, so that we find inner product Aa equal to 0, which is nothing but norm A square equal to 0. That is, norm A is 0. We know for any vector norm is 0 if and only if it is the 0 vector. So, A is the 0 vector. Next result. Let A and B be two vectors in Rn such that for each y in Rn, inner product of Ay equals with inner product of B and y. Then we must have A and B are identical. We have for each y in Rn, inner product Ay equals with inner product By. Using the additivity property of inner product, we can write this as inner product of A minus B and y equals with 0. Now, using the previous result, we have A minus B must be equal to the 0 vector, that is A equal to B. Next, another result from linear algebra. Let T from Rn to R be a linear transformation. Then there exists an unique vector V equal to V1 to Vn in Rn such that each vector x in Rn we can express Tx equal to inner product xb. Let us give a proof. Let us consider the standard frame E1, E2, En of Rn, where Ei denotes the ith unit coordinate vector for each I from 1 to n. That is, Ei is the vector which has ith component 1 and all other 0. Since this is a frame, obviously it is a basis. Now, each vector x in Rn can be uniquely expressed as linear combination of these Eis. So, we can express x equal to x1 E1 plus x2 E2 plus up to xn En. Now, Tx is nothing but T operating on x1 E1 plus x2 E2 plus dot dot xn En. If we apply additivity property, then it will be sum of n many terms. Then we apply the homogeneity. So, finally, we have Tx is nothing but x1 Te1 plus x2 Te2 plus xn Ten. Writing Vi equal to Tei for each and every I, we get this as x1 V1 plus x2 V2 plus up to xn Vn. We know we can express this as the inner product of the vectors x and the second one which has components V1, V2 up to Vn. That is nothing but inner product of x and V, where V is the n vector V1, V2, Vn. Now, T is given and our choice of Ei is unique. So, uniqueness of V1, V2, Vn are surely. So, the uniqueness of V is trivial. Clearly, the vector V depends on the choice of the linear transformation T and the frame Ei. On the other hand, if we are given any vector V equal to V1, V2 up to Vn in Rn, it is easy to verify that Tx defined by inner product x to V, obviously this is a scalar field defined on Rn, it is a linear transformation from Rn to R. Let us recall the notion of differentiability of a scalar field. Let A be a subset of Rn, F is a scalar field defined on the set A. We further assume that F is differentiable at a point A, which is an interior point of the set A. Then there exists a linear transformation T, which we usually denote by f dash A from Rn to R, such that for every suitable y in Rn, we can express the increment of f equals f of a plus y minus f a equal to f dash a y plus norm y E a y, where E a y is the error term which tends to 0 as y approaches origin. Now, T is the linear transformation. So, we search for a vector V in Rn such that for every y in Rn, we can express T y as inner product y v, that is f dash a y equal to inner product y v. The existence of such a vector V has already been given by us. We remember that for each I from running from 1 to n, Vi is T e I. So, we calculate inner product y e I. It is nothing but f dash a operating on e I, that is the vector derivative f dash a e I, and we know it is nothing but del f del x I a, and this is true for every I. Thus, the vector V is nothing but the n-tuple of vectors del f whose components are del f del x 1 a up to del f del x n a, which we discussed earlier and denoted by the symbol nabla f a. Clearly, this vector exists provided the scalar field f is differentiable at the point A. Further, it depends on the scalar field f and the point A, and since f dash a is unique, it is also unique. We shall call this vector the gradient of f at the point A, and also use another notation grad f for this. The formal definition follows. Let A be a subset of Rn. F is a scalar field defined on the set A, which is differentiable at a point A, which is an interior point of the set A. Then the vector nabla f a, that is del f del x 1 a up to del f del x n a in Rn, that is the n-tuple consisting of all the partial derivatives of f at the point A and in natural order, is called the gradient of f at the point A and is denoted by the symbol grad f at A. Now, whenever we are going to find grad f at some point A, the following formula will be very helpful. We have grad f a equal to del f del x 1 a up to del f del x n a. So, that is nothing but f dash a operating on E 1 up to f dash a operating on E n. Now, we are going to study some basic results regarding gradients of differentiable scalar fields. The first result follows. Let A be a subset of Rn and f g are two scalar fields defined on the set A such that both are differentiable at the point A, which is an interior point of the set A. Then gradient of the function f plus g at the point A equals with gradient of f at the point A plus gradient of g at the point A. Let us give the proof. First we define H equal to F plus G over the set A by pointwise principle. Since both F and G are differentiable at A, we know the function H equal to F plus G is also differentiable at the point A. And we have already proved that the corresponding linear transformation is given by H dash A equal to F dash A plus G dash A. As the scalar field H equal to F plus G is differentiable at the point A, we are assured that grad H at the point A, that is grad of F plus G at the point A, exists. We can easily check grad H at the point A is nothing but the n tuple of partial derivatives of H at the point A in natural order, that is del H del x 1 A up to del H del x n A. We replace H by F plus G, and we know from the properties of partial derivatives for every I, del of F plus G del x I A is nothing but del F del x I A plus del G del x I A. So, we put it here. We can express this as sum of two vectors. We separate those with F and those involving G. So, we have del F del x 1 at A up to del F del x n at A added with del G del x 1 A up to del G del x n A, which is nothing but grad F A plus grad G A. Now, grad F A and grad G A both are members in Rn, so their summation is meaningful, and hence grad G A is another member in Rn. Here H was a scalar field defined on Rn. We show the same calculation in an alternative fashion. We know we can express the linear transformation H dash A as the sum of two linear transformations F dash A and G dash A. Hence, for each y in Rn, we have H dash A y equal to the linear transformation F dash A plus G dash A operated on y, which is nothing but F dash A y plus G dash A y. Therefore, the inner product gradient H at A and y equals with sum of inner product grad F at A and y and inner product grad G at A y. So, this is nothing but inner product grad F A plus grad F G A with y. Now, this is true for every y in Rn. So, we can use the result we have deduced earlier, and hence grad H at the point A is nothing but grad F at A plus grad G at A. Next result. Let A be a subset of Rn. F from A to R is differentiable at a point A, which is an interior point of the set A. We define another scalar field H on the set A by H equal to Cf, where C is a real number. Then gradient of H at the point A, that is gradient of the function Cf at A, is nothing but C times grad F at A. We start the proof. Since the scalar field F is differentiable at the point A, we have H equal to Cf is also differentiable at the same point. Hence, grad H at A, that is grad of Cf at the point, exists. Moreover, we have already deduced that H dash A, that is Cf dash A, equal to C times F dash A. Hence, for every y in Rn, we find Cf dash A operated on y, nothing but C times F dash A operated on y, that is inner product of grad Cf A with y equals with C times inner product of grad F A and y, which equals with inner product of C times grad F A y. Hence, we have grad of Cf at the point A equals with C times grad F A. Combining the above two results, we can have the following. Let A be a subset of Rn. F and G are two scalar fields defined on the set A which are differentiable at a point A which is an interior point of the set A. Then for every pair of scalars lambda and mu, gradient of the scalar field lambda f plus mu g at some point A equals with lambda times grad f A plus mu times grad g A. Next we find the following. We can call this the Leibniz rule for gradient. First we state the result. Let A be a subset of Rn, F and G are two scalar fields defined on the set A which are differentiable at a point A, an interior point of the set A. Then gradient of Fg at A equals Ga times grad Fa plus Fa grad Ga. Let us look once at the right hand side. Grad Fa, that is a member of Rn, and Ga is a scalar. So, Ga grad Fa is a scalar multiple of a Ga to the vector grad Fa. So, it is a member of Rn. Similarly, the next term also. So, we are adding two vectors of Rn. Now, let us give the proof. Given the scalar fields F and G are differentiable at the point A, we define a scalar field H over the same set A by pointwise principle, which is nothing but the product F and G. That is, for every x in A, Hx is Fx into Gx. We have already proved that H is differentiable at A and hence grad H at A exists. Moreover, H dash A equals with Fg dash A equals Ga F dash A plus Fa G dash A. Now, for each y in Rn, H dash A operated on y should be equal with Ga F dash A plus Fa G dash A operated on y. To make our notations simpler, let us write lambda equal to Ga and mu equal to Fa. Then H dash A is nothing but lambda F dash A plus mu G dash A. So, it is nothing but lambda F dash A plus mu G dash A, that is lambda F plus mu G dash A. Consequently, for every y in Rn, we find H dash A operated on y equals with lambda F plus mu G dash A operated on y. In other words, inner product of grad H at A and y equals with inner product of gradient of lambda F plus mu G at A and y. Now, using the linearity property of inner product, we can write this as using the linearity property of gradient, we can write this as lambda times grad F at A plus mu times grad G at A with y. Since this is true for every y in Rn, we find that grad H at A equals with lambda times grad F at A plus mu grad G at A. Now, we are writing the values of lambda and mu. So, we find that gradient of Fg at the point A is nothing but Ga gradient F at A plus Fa gradient G at A. Next result. Let A be a subset of Rn. F is a scalar field defined on the set A and F is also differentiable at a point A which is an interior point of the set A. We further assume that Fa is different from 0. Then gradient of H at A, that is gradient of 1 by F at A equals with 1 by F square grad F at A. We mention the proof. Since F is differentiable at A, it is continuous at A. As F is continuous at A and Fa is different from 0, we can find a neighborhood of the point A in which F does not vanish. So the function h equal to 1 by f is well defined in some neighborhood of the point A. We earlier proved that the scalar field h defined by 1 by f is differentiable at A. So grad h at the point A exists. Also h dash A is nothing but minus 1 upon c square f dash A, that is minus 1 upon f square f dash A. Hence, for every y in Rn, h dash A operated on y equals with minus 1 upon f square f dash A operated on y, that is minus 1 upon f square f dash A operated on y. From this we have inner product of gradient h at A with y equals with inner product of minus 1 upon f square grad f at A and y. Since this is true for every y in Rn, we find that grad h at A equals with minus 1 upon f square grad f at A. Combining the previous two results, we have the following result. Let A be a subset of Rn, f and g are two scalar fields defined on the set A and both are differentiable at a point A belonging to interior A. We further assume that G A is non-zero. Then h dash A equals with 1 upon G A square multiplied by G A f dash A minus f A G dash A. Here h is nothing but f by g. Consequently, gradient of h at A equals with gradient of f by g at A equals with 1 upon G A square G A grad f A minus f A grad G A. So we have already defined gradient of a scalar field and studied these some properties. Now we are going to state why it is so important. Let f be a scalar field defined on a set A, subset of Rn, and A is an interior point of the set A. If the partial derivatives del f del xi at A exist for each I from 1 to n, we know to calculate the partial derivatives is rather easy. So we can easily calculate the vector gradient f at A. Now if by some means we come to know that the scalar field f is differentiable at the point A, then grad f at A will be the 1 by n matrix representation of the linear transformation f dash A with respect to the natural frames. So whenever we are going to check whether some scalar field is differentiable at a point or not, if anyhow we can imagine that it is differentiable, we can find grad f and easily calculate the linear transformation. We are discussing differentiability of a scalar field. So a scalar field is a map from some subset of Rn to R. So one particular case is whenever n is equals with 1, then f is nothing but a real valued function of a single real variable. While discussing differentiability, we defined f dash A to be a linear transformation. So whenever n equal to 1, then also f dash A is a linear transformation. But whenever one studies single variable calculus, he finds f dash A is a real number. So this is a possible point of confusion. What is the relation between these two? We shall discuss it here. Let f be a map from A to R, where A is a subset of reals and A is an interior point of the set A. If the function f is differentiable at A, we know that there exists a unique linear transformation f dash A from R to R satisfying f of a plus y equal to f A plus f dash a y plus E f a y for all suitable y, and y tends to 0 implies E f a y also tends to 0. We mentioned that from our courses in calculus of functions of a single real variable, we studied that in such a case f dash a is a unique real number. But here we found that f dash a is a linear transformation. So, how to relate between these two? So, first of all, let us denote these two by two different symbols. We shall denote the linear transformation by f dash a and the real number by df dx a. In such a case, the gradient of f at the point a exists and it is given by grad f at a equal to df dx at a. Clearly, this will be a vector in R. So, we can represent it as an 1 by 1 matrix. As f is a function of a single independent real variable, here ordinary derivative came into picture in lieu of partial derivatives. Let us consider the linear space of real numbers over the field R itself. So, it is a one dimensional vector space and the standard frame in this case is the singleton set consisting of 1. So, the matrix representation of the linear transformation f dash a from R to R with respect to these frames, we are using the word "this" because we are considering domain R as well as codomain R. So, the matrix will be df dx at a and obviously it is a 1 by 1 matrix. Hence, we must have f dash a operated on 1 equal to df dx at a. So, this is the desired relation. That is, usually whenever we say f dash a is a real number, then it is nothing but the linear transformation f dash a operated on the vector 1 of R. We further note that here we used one more thing, that sometimes we identify a 1 by 1 matrix by its entry. Actually, if we consider any y in R, then f dash a operated on y is nothing but f dash a operated on y times 1. We consider y as a scalar and 1 as a vector. So, by the linearity of f dash a, y comes out. So, it equals with y times f dash a operated on 1. So, it is nothing but y times df dx at the point A. This module we come to an end with an following note. Actually, we are giving answer to an unanswered question which we discussed earlier. Let us consider a proposition. Let A be a subset of Rn. F is a scalar field defined on the set A and A is an interior point of the set A. If from some u and v in Rn, both the vector derivatives f dash a u and f dash a v exist, then f dash a u plus v exist and f dash a u plus v equal to f dash a u plus f dash a v. In an earlier module, we proved that this is not true by citing a counter example. In that example, f dash a u, f dash a v both exist, but f dash a u plus v did not exist. So, naturally arises the question, can we find or add some extra conditions under which this is true? An answer follows. We mention a result. Let A be a subset of Rn, f is a scalar field defined on the set A and f is differentiable at the point A, which is an interior point of the set A. Then for each u and v in Rn, we must have the vector derivative f dash a u plus v equals with f dash a u plus f dash a v. That is, we are adding the condition f is differentiable at the point A. Since the scalar field f is differentiable at the point A, we know for every vector w in Rn, the vector derivative f dash a w finitely exists. We find that f dash a u plus v equals with the sum of ith component of the vector u plus v multiplied by del f del xi at A. In the next step, we write the ith component of u plus v, that is ui plus vi. So, ultimately we have summation I from 1 to n ui del f del xi at a plus another term where vi appears instead of ui. So, finally, we have f dash au plus f dash av. So, in this module we introduced a concept gradient, we studied its properties. After that, we answered some unanswered questions. Let us conclude here.